Welcome to this comprehensive guide on pairwise comparisons in Stata. This session is designed to bridge the gap between theoretical foundations and practical application in economic research. We will explore post-estimation hypothesis testing, which is a vital tool for undergraduate and graduate students to master. As illustrated in the graphic, our journey begins with identifying relationships in raw data, like the scatter plot on the left, and progresses toward the structured statistical comparisons shown in the matrix on the right. Throughout this presentation, we will discuss how to move from a general model assessment to understanding specific, significant differences between groups within your data.
In economic research, we rarely compare just two groups. We often compare multiple regions, industries, or policy levels. This brings us to the multiple comparisons trap. The more comparisons you make, the higher the probability of a type 1 error, or a false positive. Mathematically, the probability of at least one false positive is 1 minus 0.05 to the power of n. As shown in the graph, while one test has a 5% error probability, this risk escalates quickly. With 10 tests, it's 40.1%, and by 20 tests, there is a 64.2% chance of finding a significant result that is actually just statistical noise. Without proper adjustment, findings in complex models are often unreliable. To handle this risk, we must navigate different adjustment methods based on our estimation context.
Choosing the right Stata command depends entirely on your estimation context. If you are dealing with simple summary statistics without a regression, pwmean is the appropriate command. For standard linear models like ANOVA or OLS, pwcompare is the standard tool for post-estimation. However, for more complex nonlinear models such as logit and probit, or when dealing with interaction effects, you must use a combination of margins and pwcompare. These post-estimation comparisons are vital because they bridge the gap between a global model assessment and understanding specific group-level variances.
Choosing an adjustment method involves navigating a spectrum from liberal to conservative. Liberal methods, like Fisher's LSD, involve no adjustment and are meant for planned hypotheses, making significance easier to achieve, but increasing false positive risk. On the other end, conservative methods like Chaffee offer high protection against type 1 errors during unplanned exploration. Tukey HSD is highlighted as the gold standard for all pair comparisons in linear models because it balances power and error control. Bonferroni is a universal, strict choice that divides alpha by the number of tests. Additionally, for studies comparing multiple treatments against a single control, Dunnett's test is the appropriate specialized tool.
At its heart, a pairwise comparison is a linear hypothesis test. The null hypothesis, H0, is that the difference between the means of two groups is 0. Mean A minus mean B equals 0. We calculate a t-statistic by dividing the difference in predicted values by the standard error of that difference. For example, if Group A has a predicted wage of $50,000 and Group B has $48,000, we test if that $2,000 difference is statistically different from 0 given the variance in the data. However, these mathematical tests rely on several key assumptions being met. Before conducting pairwise comparisons, it's vital to ensure our model meets three core statistical assumptions. First is independence of observations, which is particularly critical for ANOVA. Second is normality, meaning the residuals of our model should be normally distributed. Third is homogeneity of variance, implying groups should have roughly equal variance, though you can use robust standard errors if this is violated. Beyond these, we must address the balance issue. In experimental settings, we often have balanced data with equal sample sizes. Stata's default for many post-estimation commands is as balanced, which treats all groups with equal weight. However, in observational economic data, we frequently encounter unbalanced data with unequal sample sizes. In these cases, it's crucial to use the as-observed option in Stata to reflect the actual sample distribution of the population. Imagine you're comparing wages between urban and rural areas. If 80% of your sample is urban, using the default as balanced would treat them as 50-50, potentially leading to misleading conclusions about the average person. Using as observed corrects for this. Now that we understand these foundational requirements, let's look at how to interpret the results for economic significance. It is vital to distinguish between statistical significance and economic significance. A tiny difference can be statistically significant if the sample size n is very large, but it might not matter for policy. Always look at the effect size. In our table, the contrast of 5.20 represents our effect size. In a linear model, this means Group A earns $5.20 more. In a logit model, it indicates a 5.2 percentage point higher probability. Statistical significance, indicated by the p-value of 0.03, answers the binary question, is this result distinguishable from 0? Finally, avoid interpreting odds ratios and pairwise comparisons if probabilities are more intuitive for policy audiences. For example, a result might be statistically significant, but the magnitude is too small to have any real-world benefit for decision makers. Now let's look at the primary command used to generate these results in Stata. The pw-compare command is used after a linear regression, or ANOV. The syntax is simple: pw-compare followed by the factor variable and then your desired options. Key options include effects for the full table, mut-compare for the adjustment method, and groups for simplified letter coding. To compare yields across fertilizers with two-key adjustment, you would type pw-compare fertilizer, effects mut-compare two-key. For more complex models, return to the margins command. When we move from linear to nonlinear models like logit or probit, the interpretation challenge increases significantly. Standard regression output provides log odds coefficients, which, as you can see on the left, are quite abstract. Stating that the log odds of success increase by 1.2 doesn't resonate well with most audiences. This is where the advanced engine comes in, combining the margins command with the pw-compare option. The syntax is straightforward: margins, followed by your factor variable, and then the pw-compare option in parentheses. This approach transforms those difficult log odds into probability differences, which are far more intuitive. As shown on the right, that same data now tells a clear story. For example, the probability of success increases by 12 percentage points. Furthermore, this technique is essential for handling interaction terms, like region #treatment, seamlessly, ensuring your post-estimation analysis remains robust and easy to communicate. When working with observational data in economics, we rarely have the luxury of perfectly balanced groups. This slide outlines a practical data preparation checklist to ensure our pairwise comparisons are valid. Step 1 is simply loading your data into Stata using the use command. In Step 2, we must check the frequencies using the tabulate command. This is crucial to see if any groups or cells in our analysis are empty, which can break our models. If cells are not empty, we move to Step 3 to check balance, using the describe command to understand the sample distribution. Finally, Step 4 is the decision point for selecting the right weighting. Option A, as balanced, is the default in Stata. It treats all groups as having equal weight, which is ideal for controlled experiments. However, for descriptive studies using real-world observational data, option B, as observed, is often more appropriate because it uses the actual frequencies found in your sample. Lastly, if you find you have missing data combinations, option C, empty cells reweight, provides a specific syntax to handle those empty cells. Choosing the right weighting method is a key step in moving from raw data to robust and meaningful economic insights. Let's look at a practical example testing 5 fertilizers to maximize wheat yield. In the Stata code provided, we load the dataset, check the frequency of our categorical variable, and then run a standard linear regression with fertilizer as a factor variable. The initial regression f-test might tell us that something is different among the group means, but as the text at the bottom highlights, it doesn't tell us what specifically is different. This visual disparity in the bar chart suggests variation, but we need post-estimation pairwise comparisons to determine which specific fertilizers outperform others statistically.
Now, let's see the practical application in Stata. We use the command pwcompare fertilizer, adding the effects option to display the detailed table, and mcompare tukey to handle the multiple comparisons penalty. This specific option automatically adjusts our p-values for all 10 possible pairs in the background. In the results table, the p greater than t column provides these adjusted p-values. Take a look at the highlighted comparison, fertilizer 1 versus fertilizer 3. With a p-value of 0.004, this result is statistically significant at the 5% level. This is further supported by the 2p interval of 1.2 to 3.5, which does not cross 0. In contrast, other pairs like 1 versus 2 or 2 versus 3 show p-values well above the 0.05 threshold, indicating no significant difference between those specific groups after the adjustment.
When you have many groups to compare, a full table of every pairwise difference can be extremely difficult to interpret. Stata's Groups option provides a much cleaner alternative. By using the syntax pwcompare fertilizer groups, Stata assigns letters to indicate which groups are statistically similar. In this example, fertilizer 2 and fertilizer 4 both share the letter A. This means they are not statistically different from one another. In contrast, fertilizer 1 is assigned the letter C, indicating a significant difference from any group that does not share that letter. This compact letter display allows researchers to quickly categorize groups into distinct performance tiers, making the results much more accessible for policy discussions or publication. In this scenario, we move to a nonlinear logit model to examine how a person's geographic region affects the probability of having high blood pressure while controlling for BMI. To get interpretable results, we use the margins command with the pwcompare option. We've also applied a Bonferroni adjustment to ensure our statistical conclusions are robust. If we look at the comparison between Region West and Region Northeast, the contrast is negative 0.037, with a significant p-value below 0.05. The translation here is key. It tells us that Region West has a 3.7 percentage point lower probability of high blood pressure than Region NE, assuming BMI remains constant. This demonstrates how marginal effects turn complex logic coefficients into clear, actionable findings. As the saying goes, a picture is worth 1,000 coefficients. While tables provide precision, plots make your results immediate and intuitive for any audience. In Stata, the marginsplot command is our primary tool for this. By using the horizontal option, we make the group labels easier to read, and xline 0 adds a crucial vertical reference line at 0. The interpretation is straightforward. If a confidence interval, those horizontal error bars, does not cross the dashed 0 line, the difference is statistically significant. Look at the blue line for region W versus NE. Because the entire interval sits to the left of 0, we have visual confirmation that region W has a significantly lower probability than the Northeast. The other two regions cross the line, indicating their differences are not statistically significant. This visual approach is often the most effective part of a research presentation because it tells a clear economic story at a single glance. Automating your workflow from Stata to Word or Excel is a key productivity hack that saves time and reduces manual entry errors. The AskDocs command, as seen in the code block, is the most efficient tool for creating instant, formatted tables directly from your analysis results. For more specialized needs, such as custom matrix formatting or specific cell placement, the Put Excel command offers granular control over your output files. By simply adding the AsDocs prefix to your pwcompare command, you can move seamlessly from the Stata results window to a publication-ready table in Word. This automation ensures that your reported data remains consistent and reproducible throughout your research process. Now, let's wrap up with a summary of best practices. To conclude our discussion, let's summarize the 4 essential best practices for pairwise comparisons. First, define your hypothesis first. It is crucial to avoid p-hacking. Plan your contrast based on your research questions rather than fishing for significant p-values. Second, select the appropriate method. Tukey HSD is excellent for balanced linear models, while Bonferroni is a reliable, robust choice for a wide variety of situations. Third, always check your assumptions. A common pitfall in observational data is having an unbalanced sample. In such cases, using the as observed option in Stata ensures your results accurately reflect the population. Fourth, visualize your data. Using command